All right, welcome back, everybody. So, like I was saying, everything, and I'm just saying this for the video, everything from this point forward should be going on to the third 9 weeks. Again, you will see some funky stuff happening with the due dates. That's okay, just ignore the due dates for right now. Just know that every homework assignment we have this week is going to be due the next day. And then once we get to next week, everything should kind of even out. You're going to see everything that's due this week. I'm going to have to make the due date on Monday. Actually, no, I shouldn't make the due date on Monday. I should make it on Tuesday because we don't have school next Monday. Go. There you go. All right. So, this whole chapter is about polynomials, right? And we had quadratics, which were technically polynomials. But now what we're going to do is expand that. We're going to say, okay, moving onward from quadratics, how can we work with other polynomials that are similar to quadratics? And how can we work with them in the same way that we had using quadratics? Okay. So we spent a lot of time factoring quadratics, right? Spent a lot of time factoring quadratics, several days factoring quadratics. So what we're going to do now is, well, how do we expand that to polynomials? Right? How do we expand that to polynomials? What we've learned so far about polynomials. Recall that if a number is divided by any of its factors, the remainder is 0. Right? If I take, say, 24, and I divide it by one of its factors, 6, I get an even number, right? Not even in terms of even odd. I'm talking about like a whole number, correct? No remainder. If I divide a number or anything by one of its factors, I get a value, no remainder, with a remainder of 0. Likewise, you could do the same thing if you're thinking about polynomials. Right? There was that example in our synthetic division notes where it came out as the remainder was 0. And we talked about it being a factor of that polynomial. This remainder theorem that you have on your paper there says that if we take x minus a and we divide it through a polynomial, and we get the remainder is 0, or if you plug it in and you get the factor that it turns out to be 0 in the end, we know that it's a factor. Okay? For any polynomial p of x minus a is a factor of p of x if and only if, so that's a biconditional statement. You know the opposite is also true as well. If and only if p of a is equal to 0. So you know that works backward as well. If you know p of a is equal to 0, then you know it's a factor. Like if you run it through synthetic division and your last number is a 0, you know it's a factor. Works forward as well. You know that if it's a factor, you're going to get a 0 in the end, right? You're going to get a 0 remainder. So let's test these things out. Determine whether this binomial is a factor of the given polynomial p of x. So I've got x plus 1, and I want to see if it's a factor of x squared minus 3x plus 1. Okay, well, that means that I run synthetic division with -1. I can do this, right? I can divide it through because it's a linear binomial, right? I can divide it through using synthetic division because it's a binomial. It's a linear binomial. Well, this makes a 1, a -3, and a +1. No zeros needed. Bring it down. Number in the box times the number below the line. Add down. Number in the box times the number below the line. Is x plus 1 a factor of x squared minus 3x plus 1? No. It is not. And we could have seen that from the very beginning, right? This is not a factor. Not a factor. If we just reasoned it through and said that, okay, are there any factors of that thing? Are there any factors of 1 that has to get to -3? No. The only factors of 1 are 1 and 1, right? So there are no whole number factors of x squared minus 3x plus 1. Okay? Well, let's check this one. That's not so easy to tell, is it? Okay. That's not very easy to tell if it's going to be a factor right away. So let's run synthetic division. What number goes in the box? 2. right? Because we would say 3x minus 6 equals 0. Add the 6, divide by 3. X equals 2. So 2 goes in the box. Make sure every term is represented. And now we run synthetic division. 3, 6, 0, 0, 6, 12, 15, 30, 0. Is 3x minus 6 a factor of that big polynomial? Yes, it is. We don't know how we got there yet. We don't know how we chose 3x minus 6. Where did that 3x minus 6 come from? That's where we'll be working in the next couple of sections. How do we find out what that factor is? Okay. And that's really what we're starting with here. We're already familiar with methods of factoring quadratic expressions. So how can we use those to relate to what we see here? Well, think back to our factoring lessons. The first thing that we would try to do is factor by a GCF. Is there any GCF in this entire thing? No. There's no GCF there. I can't factor out any sort of GCF. So then I break it down. Okay, we know how to factor something when there's 2 terms, 3 terms, and 4 terms. 2 terms, the only thing that we know how to do right now, let me write out the flow chart, right? We first start off by a GCF, and then we decide, okay, is it a 2-term, 3-term, or 4-term? I do this flow chart with my Algebra 1 students to decide, okay, what do we do from that point? Well, right now, the only thing we know how to do with the 2-term is the difference of squares, right? That's the only way we know how to factor down a 2-term polynomial. X to the second minus 4, okay, that'll turn into x minus 2x plus 2. It's a subtraction, and they're both perfect squares. 3-term, okay, we have to decide whether A is 1 or A is not 1, right? If A is 1, then it's one of those easy type 1s, factor to the last, and add to get to the middle. If A is not 1, we got to do that whole rewrite thing, and it becomes a little bit more difficult. What was the method called using a 4-term? Anybody remember? Factor by grouping. Factor by grouping. That's the only way that we know how to factor something with a 4-term polynomial. Well, is this a 4-term? So let's try it. The only thing that could possibly work is grouping. If grouping doesn't work, I can't factor this. Okay? So let's try it. Let's see what happens here if we group the first 2 and group the last 2. Well, what's my GCF of my first 2? X squared to leave an x minus 1. What's the GCF of my last 2? 25, right? And since it leads with a negative, I pull out the negative. So that leaves an x minus 1. Now, at that point, once we see that it does indeed factor by grouping, and we see it here because the parentheses are the same, I remove the x minus 1, and the leftover is an x squared minus 25. You keep having to chip away, though. Am I done? No. I see a difference of squares. See? Okay, I see two binomials, right? Two terms. They don't have any more GCF, so I can't keep doing that. So I say, okay, if it's a 2-term, I got to see if it's a difference of squares. That's not a difference of squares, but that is a difference of squares. So we could say leave the x minus 1, and then this becomes x minus 5, x plus 5. And that's my answer. Okay? How many factors does this have? 3 3 factors. What was the beginning? What was the degree of the polynomial? 3. Ooh, we might see a connection there. Okay, let's take a look at this one. I see 4 terms, right? Okay, is there any big GCF to take out? Is there any big GCF with the entire term? No. So now I got to go to 4 terms. Got to factor by grouping. Okay, I group the first 2. I remove an x squared, leaving a 2x plus 1. I remove a 4, leaving a 2x plus 1. Now, you know, it's just coincidental that, well, I guess not so coincidental. I made this happen. I made this happen so that we see how to factor by grouping. But do all 4-term polynomials factor by grouping? No. Okay, at this point, if you tried to do this method right here, and you're like, man, those parentheses aren't matching up, maybe it just doesn't factor. Right? Maybe it's just not going to work out. That's okay, too. We remove the 2x plus 1, and we're left with an x squared plus 4. Am I done? Yes. Is that a difference of squares? Yeah, I know. I tried to think that today. It's a sum of squares, isn't it? And that cannot be factored. Difference of squares means subtraction in the middle. This is an addition in the middle. So that's completely done factoring as it is. Okay. Now, remember when I said the only thing that we could possibly do with a 2-term is the difference of squares? Yeah, I kind of lied a little bit there. That's at least all that we knew how to do. Okay. We can actually factor sum and difference of cubes. Okay. We can actually factor sum. All right, SOC, sum of cubes or difference of cubes. Okay. Just as there is a special rule for factoring difference of squares, there are special rules for factoring the sum or difference of 2 cubes. We see them below. Okay, now you have these on your paper. I would commit these to memory. Okay? I would know how to do these. What's the premise here? The premise is I've got 2 terms, so it's got to be a binomial. You see 2 terms, and they are both perfect cubes. And they are both perfect cubes. What are perfect cubes? Well, in terms of a variable, it's a power that is divisible by 3. Okay? Just like a perfect square was a power divisible by 2, a perfect cube is a power divisible by 3. So x to the 3rd, x to the 6th, x to the 9th, x to the 12th, x to the 15th, and so on. Those are all perfect cubes. In terms of the number, it's one that you could number that you could cube root evenly. Whole, not number even, but whole number even, right? No remainder. Like, for example, 1. Isn't 1 times 1 times 1? It could be represented as itself multiplied 3 times. Right? 1 times 1 times 1. Think about, well, what's 2 to the 3rd? Isn't that 8? So 8 is a perfect cube. It's 2 times 2 times 2. Same thing with 27. 3 times 3 times 3. Same thing with 64. 4 times 4 times 4. 125. 5 times 5 times 5. And so on. Okay? So those are perfect cubes. Now, you have rules for both sum and difference of cubes. So this is unique to cubes. Squares, we only had difference, right? Just that last one showed us that we couldn't factor down a sum of squares, but we could factor down a difference of squares. We can actually factor down both sum and difference of cubes, okay? Because, we can work with a perfect cube that's either positive or negative, okay? We can actually take a cube root of a negative number. Now, a to the 3rd plus b to the 3rd. So this is showing the sum rule. A to the 3rd plus b to the 3rd. What you do is you have a binomial and a trinomial for both sum and difference. Binomial and a trinomial. 2-term and then a 3-term. Those 2-term and 3-term polynomials are, well, you have the cube root of a and b. Notice that this is the same for both sum or difference. Right? These things are both the same for sum or difference. You've got the cube root and the cube root. And then it goes a squared product b squared. Okay? So the rule is the same for both sum or difference of cubes. The only thing that's changing are the signs in the middle. That's the only thing that's changing. Okay, so how can we equate the signs then? What's the rule on that? Well, if it's a plus, it starts out with a plus. And then it goes negative, positive. Okay, so a sum of cubes is positive, negative, positive. A difference of cubes goes negative, positive, positive. So there's always two positive signs and one negative sign. My Algebra 2 teacher taught me this rule, and I don't know why it stuck in my head. Shout out, Mr. Rigler. He always said, when factoring the sum or difference of cubes, keep it clean, use soap. Use soap. Use soap. Okay? So he said use the soap rule for factoring. What does that mean? That means that this sign is always the same as what you had had. This sign is always the same as what you had had. So if this was a sum, it's going to be a sum. If this was a difference, it's going to be a difference. This one is always going to be the opposite of what you have. So if this is a difference, that's going to be a plus. If that's a plus, that one's going to be a minus. And this one is always positive. Always positive. Same, opposite, always positive. So, see that? So, I don't know. That stuck in my brain. Okay, here we go. Let's try it out. So the first thing I want to do is factor by GCF. That's my first rule. Okay, let's remove. Is 108 divisible by 4? What is it? 27. Ooh, good. That's a good number too. So remove a 4x as a GCF. We're left with an x to the third plus 27. Okay, I recognize those as perfect cubes. X to the third is a perfect cube because the power is divisible by 3. And 27 is a perfect cube, well, just because I recognize that it's 3 cubes. But if you wanted to, remember that you can take the cube root of something. You see that X root button? Where is it at? Oh, it's in math. That's right. You see that X root button? I also have cube root. But that X root button will take any root of. So let's just choose choice 4, though. That's the third root of 27. And see if that comes out nice. Oh, that's 3. So you can always test out a cube root of any number on your calculator. All right, so let's just drop down our 4x. And then we've got a binomial and a trinomial. I always like to set up the signs first. So keep it clean. Use soap. Same sign, opposite sign, always positive. Same, opposite, always positive. And now what goes in there? Well, we take the cube root of each one. X and 3. And then we go squared, product, squared. X squared, product of 3 and x is 3x. 3 squared is 9. Cube root. Oh, I didn't write that squared. It didn't come through. Cube root, squared, product, squared. Make sure you catch that squared. It didn't come through when I wrote it the first time, so make sure you catch that. Cube root, squared, product, squared. And that's my answer. Now, you could try to check to see if your binomial or your trinomial would factor down any more. Spoiler alert, they never do. Any polynomial will form a squared plus or minus a times b plus b squared will never factor. But you should always check. It's always a good thing to do. Let's take a look at this one. 125 d to the third minus 8. Okay, I recognize both of those as a set of perfect cubes. 125 is 5 to the third, 8 is 2 to the third, and my power on my d is divisible by 3. So this is a set of cubes, and it's a difference. I don't really care about the sign, though. Could be difference, could be sum, it doesn't matter. So there's no GCF, so I'm just going to write it out. Binomial and a trinomial. Same, opposite, always positive. Minus, plus, plus. Cube root of 125 d to the third is 5d. Cube root of 8 is 2. Okay, we got our setup for our binomial, and now I take those pieces, squared, product, squared. I take 5d squared, I get 25d, sorry, I take 5d and then I square it, I get 25d squared. I take the product of 5d and 2 to make 10d, and then I square 2 to get 4. And that's my answer. Got one more of those. Let's do one more, okay? Sound good? Good. 8 plus z to the 6th. 8 plus z to the 6th. All right. Well, I don't have any GCF, so I'm going to write out binomial and trinomial. Same, opposite, always positive. Now, my first binomial is the 2 cube roots. 2 and z squared. Sorry, my 2's and my z's. I'll do it a little curvy too. How about that? There we go. And then I'll take squared, product, squared. There's my answer. Questions about that? So now we add on to our list of things that we have to check for a two-term. We not only have to check for difference of squares, but now we have to check for difference of sum of cubes. All right, let's take a look at the next problem now. The volume of a rectangular prism is modeled by this function, where I have x to the third minus 8x squared plus 19x minus 12. I don't know, maybe the sides are set up. They're going to be, like a couple, like the length is 2 greater than its width, and then the height is 2 less than the width. I don't know, something like that. But we get the volume of this box is x to the third minus 8x squared plus 19x minus 12. That's the equation for the volume of the box. Now, it's graphed below, and you see that on your page there too. Identify the values of x for which v of x would equal 0. Then use the graph to factor. That's an interesting phrase. Use the graph to factor. We haven't really used graphs to factor, have we? Okay, so what does that mean? Well, I think the first part of what it's asking me is relatively easy. Identify the values of x for which the function equals 0. Yes, I'm asking for the zeros of the function. How many zeros of the function do you see? 3 of them. I see 3 zeros to this function. Well, what are they? I see x equals 1. I see x equals 3. I see x equals 4. Okay, and all I'm doing is just picking these right off of our graph here. Here, here, and here. I see 1, 3, and 4. Now, it's going to be very important that we understand zeros correspond to factors. Right? Zeros are factors. Zeros of the equation are factors of the polynomial. So what does that mean? Well, the corresponding 0 to x equals 1 would be x minus 1. The corresponding 0 from x, the corresponding root from x equals 3 is x minus 3. X equals 4 would generate an x minus 4 as my factor. So what would give me the entire polynomial? Well, the entire polynomial would be v of x is equal to x minus 1, x minus 3, x minus 4. Now, if I was unsure about any of those factors, what could I have done to verify that any one of those factors are truly factors? What could I have done? Well, the same thing that we did on our first page. Run it through synthetic division. If it turns out to be a 0, then it was a factor. Like, for example, here. I mean, this is the end result of this problem. We used it to factor it down, right? That's fully factored form of that. But if I was like, nah, I don't really trust myself, did it really land at 4? Or is it like 4.01 and we just don't see it? Like, because I just kind of like picked that off the graph, right? Like that could have been like, what if this was a decimal and I didn't realize it? Well, let's just double check. Let's see if x minus 4, x equals 4, is truly a root. Well, that'd be a 1, a negative 8, a 19, and a negative 12. Let's see. Okay, a 1, a 4, a negative 4, a negative 16, a positive 3, a 12, a 0. Okay, good. It was indeed a factor. Hey, what's left over when we factor out an x minus 4? What's left over after we divide out an x minus 4? Ooh. Can I factor that? Yeah. So essentially what I'm doing here is I'm taking x minus 4 and I'm factoring it out, and that's what's left over. And then I can actually, since I got it down to a quadratic, I can factor that down even more. So this turns into an x minus 1, x minus 3 that only verifies our results from our graph. So the process is figure out where your zeros are. Figure out where your zeros are. And then to be sure, run it through synthetic division. By this point, you should be very good at synthetic division. It should happen pretty quickly. So you can run it through synthetic division really quickly and then see, oh, yes, this definitely is a factor. And then you can factor it down even more if you'd like. If we get time today, I want to run through an example that shows you a little bit more about that. All right, last one that we got here. Last one that we have. Okay, if I want to factor this completely, factor it completely. What's the only method that I can possibly do right now algebraically? Grouping. Because GCF, there's nothing there. And then I would try to group. Notice how I say try to group. I've got an x squared and then an x plus 3. Okay, what's the GCF between 28 and 60? Ugh. Is it anything that has kind of come out as a 3? Because the only thing that divides 60 by, to get it to be a 3 is 20. Is 20 a factor of 28? Ugh. Is this going to factor by grouping? Ugh. Okay, so factoring by grouping doesn't work. So what do we do when we cannot factor by grouping? What do we do when we've exhausted our methods algebraically? Well, I just taught you a different method. I taught you a method of factoring by using a graph. So let's try that. Let's see what this graph looks like. I've got y equals, let me get this junk out of here, turn off my plot. Okay, let's see, x to the third plus 3x squared minus 28x. There's no x. Insert x. Okay. X to the third plus 3x. There's no squared. Insert a squared. Minus 28x. Okay, I better double check that. X to the third plus 3x squared minus 28x minus 60. Okay, zoom 6. Ooh. I don't even need to see the shape of the graph. How many zeros do I see in this graph? Looks like 3. 1, 2, 3. Now, do I know where they are for sure? I mean, I can kind of guess at it and be like, it looks like it's right there. Like, where does this look like it's at? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? So we think x equals 5. We think x equals -2, and we think -1, -2, -3, -4, -6. Are we very sure? No. So here's what you could do to be sure. You run one of them through synthetic division. Like, for example, let's pick x equals 5, shall we? It doesn't matter. You can pick any of these three. Let's pick 5. Why not? It's positive. And let's run it through synthetic division. Let's divide it out. Let's see what we have as factors left over after we factor one of them out. 1, 5, 8, 40, 12, 60. Okay, good. Is 5 truly a factor? Yes. I got a remainder of 0. If you don't get that remainder of 0, it's not a factor or you goofed. Right? Check back on the work or it's just not a factor. Okay, so that means we got x minus 5 as one of the factors. Remember, that root corresponds to that factor. What's left over? Well, x squared plus 8x plus 12. Ooh, what are the factors of 12 that add to get to 8? 6 and 2. X minus 5, x plus 6, x plus 2. So there is my fully factored down polynomial. So when you've exhausted your algebraic resources, you can now turn to your graphing calculator and find a 0, because any 0 will correspond to a root. And the nice thing about the zeros is that it's always going to be a linear binomial. The 0 is always going to be a linear binomial. So you're always going to be able to use synthetic division to factor it down. Okay, you factor it down using synthetic division, and then you see, oh, there's the leftover stuff of my function. And then once you get it down to a quadratic, it should be pretty easy at that point to factor it. All right, I'm going to turn off the video. Hope we're all having a good day. See you all later.